Hello everyone. My name is Thomas Kim. Today is April 6th, 2024. It is 8:38 a.m. I came across this playlist, Complex Analysis, by The Bright Side of Mathematics. The videos in this playlist are very useful and helpful to learn complex analysis. I would highly recommend you to watch videos in this playlist. From my YouTube channel, scroll down, you can find OpenGL Cuda, this playlist. In this playlist, OpenGL and Cuda, select 010 Cuda. In our previous episode, we defined operators for addition and subtraction for complex numbers. In my current episode, we will implement operators for multiplication and division for complex numbers. Show more, download current video source code. Show in folder, unzip it, rename 011 operators. Copy the folder, paste it in your working directory. Open up Visual Studio Code, OpenGL Cuda. From operators, complex.cu, double-click it. From the folder CEX, double-click CEX math.hpp. Ctrl-V, Ctrl-Home. I will arrange two files side by side. I will copy and paste these links. If you want to learn complex analysis, then you can Ctrl-click. By watching videos in this playlist, Complex Analysis, you can have deep understanding about complex analysis. I would also recommend this link. If you want to learn basics about topology, then this playlist is very useful and helpful. I would highly recommend you to watch videos in this playlist as well. Also, Ctrl-Home. To try my source code on your machine, you need up-to-date C++ extensions. Now, Ctrl-End. In the function test complex number 1, go to definition. In this function, we call kernel operation. This function is called indirectly through lambda g. This lambda g is passed as argument to kernel operation, this g. Now here I will remove all these things. Then auto F, auto A, auto B, semicolon, return A plus B. I will change it x0, x1, x0, x1. Auto square root f. I want to define a function square root that can take function f as argument. So square root takes function as argument. Open up this command prompt. dir cd 011 operators nvcc complex.cu on.exe std c++20 x compiler wd 4819 hyphen expt relaxed context per hyphen extended lambda. Hit enter. It does not build. SQRT is not yet defined. In this file, CEX math, if you scroll down, you can find function ABS. Copy this, paste. It can be SQRT. Then in this section, SQRT. With this, it should build. It now builds successfully. CLS N. Here, CET once. We can say SQRT F. We can call this function. This SQRT F takes F as argument. This F takes 2 arguments. So we have to provide, for example, negative 3.0, negative 4.0. Then new line. With this, we build again. CLS N. It is negative. Of course, it should be positive. We build again. CLS N. This value is square root of 7 because 3 plus 4. 3 plus 4 is 7. The result is square root of 7. We can use auto S8 CEM square root 8.0. Copy, paste. S8, we can pass S8. Please understand, we used CEM SQRT. This CEM SQRT can take function f as argument, also value as its argument. With this, we build again. CLS N. This is square root of 8. This is square root of 8. What if 9, 9, 9, 9? Then it should report 3. CLS N. Of course, square root of 9 should be 3. This square root can take function as its argument and value as its argument. This square root is implemented using call redirect. Let's see one more example. Here, auto H type name ARG types requires size of ARG types should be 3. Then ARG types ARGs semicolon return ARGs. This is fold expression. Copy, paste. Now I. This is multiplication. Auto T CM EXP. This EXP is defined here. Again, using call redirect. The end target is exponential function. Here 3 times h plus I divide 5. T is arbitrary exponential function. CT once T, this T takes 3 arguments. H and I takes 3 arguments. So we pass 3 arguments. For example, 1.0, 2.0, 3.0, and there we build again CLS and T. This is the result. Or we can say H plus I. We can make arbitrarily complex function or expression on the fly. With this CLS N, we have the result. T itself is a function. I explained how to create all such things through 2 or 3 videos. I implemented all these things through 2 or 3 videos in my Korean channel. Sadly, I explained how to implement call redirect, evaluate, Cuda bars, all these things in my Korean channel. I will explain how to implement these things in English in some future sessions. With this, we can solve many mathematical problems. Now, let's get back to our business. Right-click, split left, then drag this document here. So, we are viewing cex_math.hpp, cex_math.hpp, 2 views of the same file. On the left-hand side, if you scroll down, you can find class complex, ELE type, ELE type. On the right-hand side, if you scroll down, you can find class complex, real type, imaginary type. This class inherits from standard complex implementation. In this case, real type or imaginary type can be function. On the left-hand side, scroll down. In this section, device, or conjugate, constant, no except, return, complex, this, real, negative, this, imag. This is complex conjugate. Now, on the right-hand side, if you scroll down, here, I would say end of class complex real type imaginary type. Here 2 underscore device or conjugate const no except using namespace CM operators. We need using namespace CEM operators declaration or imag -1 times this m imag return complex real type 댓글 type imag type semicolon. This m real part does not change. Imaginary part is negative of current imaginary part. We need this because of class name injection. We have to specify template arguments like this due to class name injection. With this, we build again. Of course, it should build. Now, here, end of class complex ELE type, to underscore device or ABS const no except return std ABS. This returns the magnitude of a complex number. Now in this section, to underscore device or ABS const no except using namespace CM operators return CM SQRT M real times M real plus M imag times M imag. Please understand M real and M image can be functions, so we are returning function. We return a new function. In this case, we return a new value. Of course, it can be CM. With this, we build again. Of course, it should build. Now, to underscore device or nom const no except return std nom. This here to underscore device or nom const no except. We will simply copy this part, paste it here. We simply return this. This is magnitude squared of a complex number. Same is true. I haven't implemented this function yet. With this, we build again. Of course, it should build. Now we are ready to define multiplication and division operators for complex numbers. I will close this window. Scroll down. You can find namespace operators. In our previous episode, we defined operator addition and operator subtraction. Now, copy this, paste. This is operator multiplication. In this part, A real times B real minus A imaginary times B imaginary. This is real part. A real times B imag plus A imag times B real. Because we are in the namespace operators, we don't need to declare using namespace operators in this part of the code. Now copy these, paste. It is division, division, division. Here auto C A times B conjugate. Here C real B nom C imag B nom. We create new complex number. Please understand, A can be any complex number. We will build once again. It should build successfully. Please take note. We defined operator for division, also operator for multiplication, operator for subtraction, operator for addition. We defined for function template for operator functions, only for, and we took advantage of compile time branch. We defined for function templates for operator overloading, and we used only compile time branches to fully take advantage of SIMT or single instruction, multiple threads. We used only compile time branches to fully take advantage of SIMT or single instruction, multiple thread. With these things, I will arrange side by side. Now copy up to this point, then comment out, paste. I will delete all but this, like this. Now auto P CM complex 2 negative 7 auto QCM complex auto X1 auto X2. This is lambda. We simply return X1 plus X2. Then we can pass scalar like this. So P is complex number. Also Q is complex number. This is real part. This is imaginary part. Real part is a function. Imaginary part is a number. In case of P, both real and imaginary parts are numbers. In case of A and B, these are standard complex. Cuda type category A, Cuda type category B, Cuda type category P, Cuda type category Q. With this, we build again CLS N. So basically A and B are standard complex. A and B are standard complex. P is complex with 2 plus 2, 7. These integral types are converted to float. In case of Q, this is real part. This is imaginary part. Please understand A, B, P, Q. These have different types, but still complex numbers. With this, disable it. Although X, Y, Cuda, bars, we create 2 more operable variables. Right-click, go to definition. In this function, we create lambdas. I will change the name of this function. I removed S. It should be, we will build once again. It should build successfully. Now, 오로지 CM complex. X is real part. Y is imaginary part. Auto F 2 times Z plus P over Q minus 4.0. F is arbitrary complex number. CET A out. Of course, we can do A divide B plus 7.8. AB, these are standard C++ complex. PQ, these are defined here. Z is complex number. We can say F equals F real. We pass argument for xy and x1, x2. For example, 1.0, 2.0. We need imaginary part. I would set parentheses here, then comma, then closing parentheses with a line break. I will remove blank space. We build again. CLS N. So we created complex number whose elements are functions, then evaluated like this, all in parallel. Please understand, all these things work. Just defining 4 operators, just 4.